Excuse me, sir.
Yeah.
Sir, yesterday was my first quiz on Moodle. I have never given quiz on Moodle before. So I did submit the responses like 1 minute before the time was up. But later I found out that my answers were not registered. Like when the grading came up, so I saw that none of my answers were registered. Like it was showing that I have not submitted. Moodle shows it.
So you could have sent a mail then, right? Why did you wait for 24 hours to tell me this?
So I thought I would tell you in the class directly.
No, some 2 or 3 other students had this problem. I asked them to submit, and they submitted whatever they had done immediately. Now, after one day, I don't know what
Oh,
mistake
no,
was.
so it's fine. Like so if from next
Yeah.
time if happens, then I will just mail you the on spot. Okay, sir.
Yeah.
Okay, sir. Thank you, sir.
Okay, so till now we were looking mostly at some theoretical background regarding this pack learning and so on. So let's get started with actual deep learning models, which is in some sense the main focus of the early part of the course. So deep neural networks, right? So most of the time when we talk about advanced machine learning, this is what people are really interested in. So just to remind you, so we start the study of neural networks with these things called perceptrons. So a perceptron is essentially a linear separator. So you have this boundary which is defined by this kind of a so we have this hyperplane, right? So you have the weights W and the bias B, and the input vector is X, and then it will compute X transpose W plus B, and depending on whether that value is positive or negative, it will classify yes or no. And the perceptron algorithm essentially will find these weights from the training data if the data is linearly separated. So the generalization of a perceptron is to have a network of perceptrons, but as we have seen in the earlier course, if you just take a kind of cascade of linear functions, you will still get a linear function. So all these extra nodes that you have defined in between collapse into a more complicated linear function connecting the input and the output. So you can as well replace this whole thing by a single perceptron, so it doesn't really help. And in particular, there is this XOR or exclusive OR function, which says that I have two inputs X1 and X2, and I will output a 1 whenever the two are of opposite value. So either X1 is 1 and X2 is 0, or X2 is 1 and X1 is 0. And this XOR function, intuitively, you cannot draw a line which separates the zeros and the ones, you can see, but formally you can argue that it's not possible. So therefore, linear separators, unless you do some, as we know, some transformation in terms of kernels and these kind of things, linear separators don't generalize to the kind of boundaries that we want to. So as a result, we need to get to some non-linear functions. And the way we do that is to tag on an activation function. So we take our linear output Z, okay? And then this linear output Z, we then pass it through another function, sigma of Z. And this A typically denotes this activation output. So it is the transformed linear output. So this part of the perceptron is the same as before. You have Z is this X transpose W plus B or WX plus B, depending on how you want to write it. And then you do this, and traditionally the sigma is actually, the reason we write sigma is because actually it is the sigmoid. Right? So this is the same function that we use for logistic regression. And it's the smooth step, right? So this is the sigmoid function. So as the input varies from minus infinity to plus infinity, it goes from 0 to 1 with a step at 0. So this has been the way that neural networks were traditionally made more general. And then you can argue that with this kind of an activation function, you can compute more or less any separating boundary. So this then becomes the model that we want to work with. So these are, for the moment, what we call feed forward neural networks. Later on, we will see that if you allow feedback, then you can do different things. So it's an acyclic network. So the feed forward means that all the outputs go in only one direction. So there is only paths from here to here, right? So there is no edge coming back from output to input. So there are several things that you need to specify, right, in order to describe this network fully. So in no particular order, the first thing, of course, you need to talk about is how the network is connected. So we have traditionally seen in the earlier DMML course that we assume a kind of complete connectivity. So we just specify the number of nodes in each layer and we kind of arbitrarily connect everything to everything. So we assume it's a completely connected graph. Now we will see later on that we can also deal with more effectively if we restrict the connectivity and the structure to be of a particular. Then you need to decide, of course, how you are going to make the decision, right? So you need to decide this output layer, what is the function that you're going to use in order to get your final classifier or whatever you're going to do. Right? So then because of gradient descent, you need to decide, this is what we discussed last time, that depending on the kind of system you're dealing with, you have different choices for loss function. So you have to choose the loss function. And most importantly, along with the network connectivity, you have to decide also whether you want to do sigmoids or something else. And finally, there is this problem of initialization. How do you start this off? Because you need to set some values at the beginning before you start learning. So how do you actually do that? So we saw last time in the last course that training this network is done through back propagation. Okay? So you, just one second. So the way that back propagation works is it uses the chain rule, right? So it uses the chain rule in order to compute these gradients. So in the forward direction, you first exercise the network, right? So you compute all the linear and non-linear outputs. So the Z's are the linear outputs and then A's are the non-linear outputs. And then with respect to every weight and bias in the network, you want to compute the gradient of the cost with respect to that, and that you get by the chain rule. So you can first compute the variation of the cost with respect to the linear outputs, and from that, because the linear output is a linear function of the input at that point, you can compute the derived thing in terms of weights and biases, right? So this is this forward pass and backward pass. So you compute the outputs and the activation values, and you backward pass, you use the chain rule to compute all the gradients in one step. And in particular, because this is usually done with a large network and with a lot of input, you don't wait for a full cycle of your training data to do an update. So you use this mini batch form of stochastic gradient descent. So you create small batches of inputs. So the small batches could be 32 or 100 or whatever. And you run this network through that many inputs in order to compute the gradient. So then you use the updated gradient, use the gradient to update the things, and then you do the next mini batch. And then you typically run this through you don't miss any input. So you run an epoch, which is a set of mini batches that covers the entire training data. So this is the traditional way that you train a neural network. Okay. So the main complication is that this is computationally very intensive. So it takes a long time for it to converge. And one of the reasons that it takes a long time for it to converge is because these gradients are unstable. So they may disappear or they may become very large. And then if they disappear, if you have vanishing gradients, as we will see, what will happen is that your changes in your parameters are very slow. So therefore your learning will be very slow. Exploding gradients we will not encounter directly, but if you had an exploding gradient, what will happen is that you have a lot of oscillation in your parameters. Right? Your gradient will suddenly say you must shift it in the positive direction by a large quantity, and then you overshoot, and then you come back. So we will look at this also a little later on. But this is really what I want to be addressing next, which is how do you deal with some of the known problems of training these neural networks. So the most fundamental issue that had been the kind of bottleneck of using neural networks. So neural networks themselves exist for a long time. Okay, so you must remember that back propagation itself, which was considered a great advance in neural network technology, dates from the late 1980s. So back propagation is already like 35 years old. And therefore neural networks, so perceptrons, remember, are from 1950s. So it's like 70, almost 60 years old. And now you have back propagation was 35 years old. So there was a lot of scope for using neural networks, but because of this instability and the computational difficulty about using them, neural networks are not really popular in the 1990s. They became popular only around 2010 or so, because only then people started understanding a little better how to control these, and also computational power at the same time became available through GPUs and things like that. So the main issue that was really holding people back was how to deal with this unstable gradient. So the most common manifestation of unstable gradients is this notion of a vanishing gradient. So the thing is that if you have this network in layers, right? So as you come backwards, right? So the gradient here depends on the gradient here. So remember that you have the chain rule. So you're multiplying a lot of values in order to get the dependency of, say, a W here on the cost here. And these values are small. So as you keep multiplying a lot of small values, as you go towards the left, okay, so traditionally in a deep neural network, this is the low end and this is the high end, right? So this is the input end and this is the output end. So the higher layers typically refer to the layers which are closer to the output, and the lower layers refer to the layers which are closer to the input. So as you go to the left, your gradient, because of this multiplication that you use in order to get these quantities, it becomes smaller and smaller. And then if you have a very small gradient, remember what you do is you take your old W and then you add some small step multiplied by the value of the gradient. So if everything is small on the right hand side, if both these quantities are small, if you have a small multiplier and a small gradient, then W hardly changes. So therefore it takes a lot of time for the initial layers to move from whatever values they were and actually acquire the trained values that you would need for your classifier. So this is this vanishing gradient problem. Now, in cases where you actually have feedback, where you have edges going back, so these are called recurrent neural networks, okay, which you will see later on in the course. This could happen the other way around, as I said. So you could actually have a gradient which becomes very large. So even a small step with respect to the gradient changes the parameter in a large way. So I'll just draw you a picture. We will see this picture later on, but this is what happens if you have a very kind of large step. So supposing I'm here on the left hand side, and this is my cost function, right? And this blue is representing how my cost function varies according to the parameters. So if I take the gradient at this point, right, it will tell me to go down. But go down by how much, right? So supposing I go down by too much, then what will happen is I overshoot and I go to the other direction, but higher up on the thing. And now I have the gradient telling me again to go down. But again, if I use too large, so here the problem is not the gradient, right? The problem here is with if I have too large a multiplier. But the same principle you can imagine happens with the gradient. So I actually start increasing my distance away from the optimum rather than decreasing my distance, as I would expect with gradient descent. So this is more or less the problem that happens with exploding gradients, but this is something which will come up only in the context of more complex models. Usually when we are talking about the type of acyclic feed-forward neural networks that we have been looking at so far, the real problem is vanishing gradients, okay? But in general, because both are possible, right? The real problem is instability. The problem is that at different parts of the network are converging at different speeds. So the usual thing is that the higher end is converging faster and the lower end is converging slower. But because the lower end is going to eventually change, the higher end is not stable in that sense. So the values it has converged to will have to keep updating based on the lower end. And in the exploding gradient problem, we'll have the reverse problem. But the lower end will keep changing rapidly and then everything will get messed up. So why is this happening is the question. So in a sense, this was theoretically answered only as late as 2010. So these two authors, Xavier Gloro and Joshua Bengio. So Bengio is one of the 3 people who got a Turing Award for working with neural networks. So we have Bengio, okay? And then we have Jan LeCun, okay? And then we have this, what's his name? Escapes me at the moment, but the guy who did backpropagation. Right? So these 3 are the 3 Turing Award winners for working with neural networks. They got the Turing Award about 4 years back. Right? So what Gloro and Bengio said is that the problem is really that traditionally, right, people were using this sigmoid as the activation function. And the motivation for using sigmoid as the activation function really came from the same motivation as neural networks. So why are we using neural networks? Because in a sense, this whole thing is driven by our attempt to understand how we think and learn. So our brains are wired this way, right? We have these neurons which fire at thresholds and they are connected together as networks. So probably this is the best way to design a system that learns. I mean, that's more or less the justification for neural networks theoretically. Because now we have what we are looking at now are called artificial neural networks, but this was the original motivation for looking at these networks at all. And typically our neurons in the biological neurons fire in this kind of a sigmoid way. Okay? So therefore it was assumed that this should be the correct notion of a non-linear activation for artificial neurons as well. So that is one aspect. And the other aspect is now everybody understood also that because of symmetries and all that in a network, we need to break the symmetry. So we need some kind of random values at the beginning. Otherwise, if you have identical connectivity and identical initial values, then you will more or less have identical progression of values as we go through backpropagation. So that multiple neurons will be serving the same purpose and not really helping us to learn. But what is the natural way to randomly initialize? Well, again, the traditional assumption was you take a normal distribution with mean 0 and variance 1. Right? So something which is centered around 0, right? And it stays close to the range plus minus 1. So the problem with this is 2 things. One is that it turns out that if you start with this at the initial stage, then this variance, as we do this forward and backward propagation, the variance actually starts increasing, especially going forward in the network, the variance grows. So when you go to the later nodes in the network, after some time, their weights are pushing the whole thing either to a large positive value or to a large negative value. And that coupled with this sigmoid gives you a problem because we already observed last time, the last course, that the sigmoid at both ends has got 0 slope. So therefore, if you have now saturated your activation function, then the gradient is going to be very small. And therefore, you're not going to be making much progress, even if you're at the wrong end. Supposing you should be here, but you're actually here, right? You should be at +1, but you're at 0, then you'll have a problem, right? So this essentially was deemed to be the informal or formal, in a way. They also mathematically derived why this should be the culprit. But this is what they addressed as the main source of this unstable gradients and something to be tackled.
Sir?
Yeah.
So the reason for variance to keep increasing is that the summation keeps happening in the consequent layers?
Yes, correct. So it's just adding up. So that's basically what they're going to handle, as I'll show you.
Okay.
So if you don't want this signal to blow up, so remember it's going in 2 directions, right? So you're doing the output calculation in the forward direction by adding up the contribution of all the inputs, but you're also doing this gradient calculation in the backward direction, which is also kind of summing up things but multiplying them as well. So it should not do anything strange. You should not die out in the reverse direction. You should not explode in the forward direction. You should not saturate. You want to avoid all these things in some sense in order to make your neural network learning more stable. So what they said is that they would like these gradients to have equal variance before and after flowing through a layer in both directions. You know, technically, so basically, if I draw a layer, right? If I draw, say, one neuron and it has some inputs and it has some outputs, right? So they would like the variance across these things to be the same as the variance across these things. And in principle, mathematically, if you want to get that, you have to actually guarantee that you have exactly the same things coming in as going out. So the layers all have to be uniform in size. But even if the layers are not uniform in size, right, what they said is you have to focus on this number of things which are contributing. So you don't want the thing to blow up, says whoever it was who made that comment. You don't want the thing to blow up. So you need to scale things by the amount that they're likely to blow up because of the addition. So this is this fan in and fan out, right? So fan in is the number of incoming edges to a neuron, and fan out is the number of outgoing edges from to the right in our neuron. So they said, well, just take the average of the two, right? So take the sum of the input incoming edges and the outgoing edges and divide by 2. And then they said, use that as your variance. So continue to use this Gaussian that we were using before, but instead of saying that the variance is 1, okay, reduce the variance at each individual thing to be 1 divided by this average fan out. So the fan out is going to be typically more than 1. So therefore, this is going to be a smaller variance than the original thing. And this is the case if you're using a Gaussian, but there is no requirement actually to use a Gaussian as the random function. So if you use a uniform distribution, for example, then you might want to choose the range of the uniform distribution. So the Gaussian is going to give you 0 plus minus something with this variance determining how much their plus minus is, right? So similarly, in a uniform distribution, you say you want to take a value uniformly at random between some minus x and plus x. So what is that minus x? What is that plus x? So they said choose this R, the range of your uniform distribution, to be this mysterious thing. Okay, it's square root of 3 divided by the average fan out. Now, why these numbers? Well, it is justified in that paper, and I'm not going to get into it. But for various things, you can kind of, under certain assumptions, you can come up with these optimum calculations. But the point is that you can use different random functions, but the main thing is that the parameter that you use of interest to constrain that random function depends on the fan out and fan in of the individual node. So this is going to be therefore not a uniform, not uniform in the sense of uniform distribution, but not the same initialization everywhere in the network, right? So for each node you will calculate separately its fan in and fan out, and according to that, you will initialize it with a slightly different. So in the same layer, maybe you'll have the same, if it's a kind of completely connected thing, in the same layer, maybe all of them will have the same parameters. But across layers, you will have, in general, even if you're using this similar type of function, either a Gaussian or a uniform distribution, the actual parameters will vary according to the structure of that layer. So this was their insight. Okay, so this is depending on which. So these are available in all the packages which implement neural networks. So it's either called Xavier init or Gloro initialization. So if you remember, this guy's name is Xavier Gloro. So it's named after the first author of that paper. Right? So both these possibilities are typically available. So when you set up a network in whichever library you're using, you can choose the initialization for every layer. And you can choose, for instance, this Gloro initialization. And if you choose the Gloro initialization, then this parameter will be automatically determined from whatever you have specified as the structure of the network. But this, remember, is right. It's 2010. Now it turns out that Jan LeCun, who is one of the other heroes in our story, right, had actually suggested this 15 years before, except that he had not used the same calculations that these people had. So he had just said, essentially taken the idea that if your input is what is going to be added up and then propagated to the output, then you use your input fan in as your denominator in these equations. Okay? And of course, if you have a uniform thing in which the fan in and the fan out are the same, then if you add fan in and fan out divide by 2, it's the same as the fan in. Right? So therefore, It can be the same if you have identical layers, but if you don't have identical layers, then this is slightly different from the earlier thing. But the point is that this was known, right? So this Jan LeCun's thing was not a secret. There were other people who had actually used it and they found that it worked well in practice. But I think till this paper by Gloro and Bengio, there was no justification in some sense why this works. And we will see soon as the next part of this thing, we will look at other activation functions other than sigmoid. So depending on what your activation function is, there are other proposals for good initialization. So for instance, if there is something called a ReLU, which we will look at, a rectified linear unit, then instead of 1 by fan-in, which is what is proposed here, okay, you can do 2 by fan. Now again, some of this is mathematically justified, some of it is empirically justified. So you have to take it with a pinch of salt, but you can, in a library that implements neural networks, you can choose. So you have to decide which one of these you want. Do you want to use LeCun initialization? Do you want to use Gloro initialization? Do you want to use this Hay initialization? And there are others also. So this is one of those hyperparameters, right? We talked about hyperparameters. So hyperparameters are these choices that you make, which typically are not to be learned. These are choices that you make, which will decide how the model will perform. And you have to choose them wisely based on experience or by some search and, look for some optimum combination of these parameters. So the choice of the initialization function is driven by this requirement to reduce the variance. And there are multiple possibilities which people have come up with, and you use one of them. So the other part of the story is the sigmoid exercise, right? Yeah.
Sir, sorry for the interruption. Sir, so earlier you said that we are doing this because the variance was not constant, like it's increasing. So yeah, even after doing this, there is some variance and that will add up. So the variances will increase, right?
Well, what you're saying is you're trying to average out the increased variance across the inputs and passing it on, right? So you're trying to balance it out. We will see a little later on that you will try to do something even more direct on this. But even if the variance goes up in one thing, remember you're taking this 1 by fan-in, right? So you're basically dampening that variance at every point. Right? So you have some variance which is coming in from these different directions, right? And then you're passing it on as a sum of these things, right? So you're doing summation of, basically you're doing w dot x, right? So now this weight thing, if you're dividing this thing by the fan-in, then you're reducing the effect of the variance. Yes. That's what we're trying to do. So there's no guarantee, but that's the intention, right?
Like we have normalized.
Yeah. So you're really trying to normalize. You're right. You're trying to normalize it at every point. But remember that this is only happening at the initialization. So this is not a continuous process in some sense.
Oh,
right?
okay.
So initially, you're doing it this way so that later on, because this is only initialization. What I talked about is only the initialization phase, right? It's not the ongoing computation. So we will see that in a minute.
So none of this thing will happen in the hidden layer. That will only happen in the first layer.
Which?
Like that. Like this averaging out.
No, it'll happen everywhere, right? Because when you take a network, right? So let me go back to wherever that network was. So you have to initialize everything in the network, right? You can't just initialize so everything has to have a value. So all these nodes also have to have initial values, right?
Okay.
So everything has to have an initial value. So what initial values you put? Earlier, it was suggested that you randomly initialize each in a kind of in the same way, right? You take a uniform, not uniform is a bad word, as I said. So you take everywhere you take, say, a normal with mean 0 and variance 1, and that doesn't work. So what they're saying is that if you have densely connected things with a lot of things coming in, then you should reduce that variance in the initialization. If you have less connections, then you can increase the variance and so on. So in a sense, all of these will have a similar thing. All of these will have a similar thing, but they'll be different from each other.
Yes. Yeah, got it, sir. Thanks.
Yeah. So initialization we looked at. Now the question is that why are we using sigmoid? Right? So the problem with sigmoid, independent of so as I said, you can control that variance blow up to some extent, but you can't guarantee that this variance is not going to blow up. And you're going to hit this bottleneck, which happens because your outputs saturate. Right? So the real problem with sigmoid is the saturation at both ends. That you have this kind of flattening out at both ends. And that says that beyond a certain point, your gradient vanishes for that reason, and therefore you're not going to get much change. So if all you need is non-linearity, then the simplest thing is just to break the line at some point, and this is this rectified linear unit. So the rectified linear unit basically says that the negative part of your line, so the line would normally have continued this way, right? So this is my x-axis. So where y-axis. Okay. So the part that goes below the line, okay, you just flatten it out onto the x-axis. So you take max of 0 z. So as long as z is positive, you get z. If z is negative, you get 0. Now, one advantage of this is that numerically it's easy to compute, right? It's much easier to compute max of 0 z than it is to do 1 upon 1 plus e to the minus z. It is not a great function to apply gradient descent to because you have this problematic thing here where you don't have a defined derivative, because on one side the derivative is 0 and the other side the derivative is whatever is the slope of that line. But in a sense, you don't really need to, you can avoid computing the derivative at that problematic point. Right? You're always at some value which is either on this side or on that side. So you'll either get the 0 slope or you'll get the real slope. So actually it turns out that this non-differentiability, so I mean, there was a lot of theoretical prejudice against such functions, but in practice it doesn't matter. And the great advantage is that it's going to be functionally much easier to compute. Right? So this is the ReLU, or the rectified linear unit. So the ReLU, but the 0 does create a problem. Okay, and the reason that this ReLU creates a problem is that if your outputs are negative, okay, then your gradient starts becoming 0, right? So if your z is going to give you a negative output, then your activation, the A, is going to become negative. And once you go into this negative zone, your ReLU has 0 slope. So that means that if you have a large part of your network which is producing negative outputs at the nodes, then at all these points, the gradient has actually gone to 0. It's pretty much like this saturated case in the earlier one, right? But this means that your network is operating, it's like having a lot of light bulbs switched off in a room, right? It's fused bulbs in a room. So your network is dying because of the fact that all these things are in this range. So one solution to this, right, is to not let it go negative, but to allow a small slope. So instead of having max of 0, z, right, you could take a very small number, alpha, and you make it alpha z, z. So now if I have a negative thing, so supposing alpha is just for hypothetical, so it's my 0.1, then if z is -1, sorry, alpha z is -1 times 0.1 is -0.1. So technically alpha z is bigger than z. So as long as alpha is a quantity smaller than 1, alpha z and the negative thing will be bigger than z. So you will get alpha z instead of z. And so you will get a kind of narrow sloping line. But the advantage is that this will not go to 0. So neurons will have slower learning in this part because your gradient is going to be lower, but you're not going to have 0. Okay, so this is called a leaky ReLU. Now, normally this alpha would be set by you as a hyperparameter. So you decide what you think is a good alpha, or you can try different values of alpha and see what good alpha works. So it is technically a hyperparameter. Now, there have been experimental ways to heuristics to deal with this. So one of them is to make this alpha actually random. So you pick alpha from some range. You fix the alpha to be one constant value. So you keep varying alpha as your training. So at different points, you choose different alphas from a range, but you don't make it too large, don't make it too small, but you don't keep it at a fixed value. And then when you're actually running your network, then you have to choose a value to use. So you can take the average of all the values that you used when you were training the network. So you pick alpha from a random range using training, and you use an average of these when actually using the network for testing it on your test data to see how well it's doing. And this seems to work well, okay? And it also acts as what's called a regularizer. So remember what regularization is. Regularization is basically smoothing out. So it makes your model more general, right? So it seems to help independent of, so the main aim of putting this random leak was to make your gradient descent more reliable and fast, but it also seems to smoothen out the model that is learned from individual quirks of your training data. So it seems to work well as a regularizer. So many of these things are, as I said, they're empirical. So I cannot justify to you why it should work as a regularizer. Okay? So it does work as a regularizer, but why it's a different matter.
So
yeah.
So we had universal approximation theorem in the end of last semester. So it was possible because of the non-linearity that we had in the functions, right?
Yeah. So that particular one, the one that we had constructed, was using that sigmoid.
Yes.
But you can do this with any, because as we saw, I mean, if you also remember before we did universal approximation theorem, okay, we had also shown that you can do XOR with ReLU.
Yes.
And so in a similar way, if you can construct things with, you use different constructions. So depending on whichever nonlinear thing you do, you can use a different construction and come up with a similar kind of a theorem.
Yes.
So it doesn't really matter. Yeah.
Yeah, like diagrammatically also I can think of building a tower from a ReLU or a leaky ReLU.
Yeah.
The only thing is that it feels this would be a worse approximator compared to sigmoid, but sigmoid has that saturation problem.
Yeah, anyway, that approximation theorem is only a mathematical curiosity, because as we said, you typically end up there building a very shallow and flat network, right? So what that approximation network does is it creates this intermediate thing.
Yes.
So this whole layer approximates your function from left to right, top to bottom in some sense, and then it produces an output like this. So you get this two-layer network in some sense, one hidden layer. So it's not really the way that you're going to build it. So again, it's more a theoretical explanation of why it suffices to use this, but that's not the best possible way to realize a boundary. So that's why we go deeper, because one thing is that there are many more parameters to learn. So this is much harder to train. Right? And second thing is that you need a much larger network also to get the desired accuracy than you would if you did it in depth this way.
Yes.
So you should not, yeah. So there are these, what should I say, these different justifications which don't really fit. So like last time in this theory thing we were talking about, even in the previous lecture, when we were talking about sample size and ideal sample size, and we talked about this VC dimension for, yeah. So now that's all good to know in theory, but as we said, you can't really look at a given neural network and easily estimate its VC dimension. So if you want to know what is the size of the training sample that I need for this network or for this problem domain, it's not really feasible to go back to the theory and try to get it. So the theory only helps you to, so in the same way that the previous lecture, what we were talking about pack learning, gives us some mathematical confidence that there is a possibility of starting with training data and building a model which generalizes. But it doesn't concretely tell us in every situation how to do it. Similarly, that universality theorem says that this network of nonlinear nodes can approximate arbitrary boundaries, but it doesn't tell us what is the best combination of nodes to do that with. So there's just it's more an existential proof, but it's not a constructive argument telling us how to do it.
Okay, fine.
Right. So now in this, coming back to this ReLU world, so what we said is you can first start with a leaky ReLU where you make this parameter an arbitrary hyperparameter that you search and fix, or you can have it varying in a range, and then in that range that you use the average. And of course, the most extreme thing, yeah.
Sir, here in this case, I think the alpha should lie between 0 to 1, more than 0, but less than 1.
Yes, yes. So that's what I said before. So alpha should be magnitude is positive and magnitude less than.
Yeah, positive and yeah.
Yeah.
Hmm.
So I had given that example 0.1, but yeah, you're right. So basically alpha should be between 0 and 1. So ideally it will be quite small, much less than 1, but it will be something so that the negative number remains a negative number. So that's the point.
Otherwise, it will like overshoot that y equals to
Yeah,
x curve.
correct, correct. So you don't want it to go like this, right? So the other thing that you can do, so this is, so if you remember, I had earlier shown you this initialization function for ReLU. So this 2 by Fanning. So that same paper, okay, so actually they define what is called a parametric ReLU. So what they say is you learn the slope as well. So you make the slope one of the parameters. So you can actually learn, they showed in this paper, you can actually learn this leak, right? And if you learn the leak, then you might get a much tighter model than you get for the other things. But the danger of this is that you actually get something which can be very over precise. So you can get overfitting. So these are some variations on this ReLU, but most of the time people just go for the plain ReLU or they go for this leaky ReLU with a fixed alpha. Okay, but again, when you are using a library, you might have a choice of multiple versions of ReLU available to you as the activation function for these interior nodes in your network.
So over here,
Yeah.
alpha means that alpha for each neuron.
Yeah, so for every neuron, basically the output function is, alpha is typically in this case a uniform value across all the neurons, right? So earlier we were saying for the ReLU that you take this as your output. You take your nonlinear, you take a linear output Z and you transform it as max of 0, Z everywhere. So everywhere the negative part gets cut off. Right? Now here you're saying everywhere you put this alpha and everywhere the negative part gets kind of reduced in slope, but it remains non-zero. So you have some small slope. So the question is, what should that alpha be? So the alpha is obviously going to be a positive number between 0 and 1, so that this slope kind of gets reduced and but stays negative. But what we are saying is that you can either fix the alpha once and for all for every neuron, or you can pick alpha randomly. Now pick alpha randomly, again, you can do it in many different ways. You can pick alpha randomly for each neuron, or you can pick alpha randomly in each cycle of your back propagation. And eventually you have to use some alpha. That's the point, right? When you're running the thing, you have to see, when you do the forward pass, you have to compute this A. So you have to use some alpha for that. So what alpha do you use at the end? Because you use a large number of alphas during the training period, because each time you're picking one at random. So what they say is you pick all these alphas that you have chosen, you keep track of them and you take the average. Okay. Now why this should work, I mean, it's not very clear, but it does seem to work. And the last one, as I said, is that you actually compute, you use alpha as a, so notice that this is part of your activation, right? So you can compute the dependence of your output cost on alpha, and you can learn alpha. And if you learn alpha, you get a much more precise model, but it sometimes, for small data sets, it might be too precise. So you can actually end up overfitting because of fitting this alpha too. But these are all just variations on this linear ReLU. And there is a kind of non-linear ReLU, which is called an exponential linear limit. So what this does is it takes this negative part and it tapers it off, right? So when Z is less than 0, when Z is greater than 0, you're still taking Z, so no problem. So this part is the line, right? When Z is less than 0, you're taking e to the Z minus 1 times alpha, right? So now e to the Z is some small quantity, right? And because Z is negative, right? So so you can see that as Z goes to minus infinity, right? Then e to the Z is going to go to 0, right? So therefore this quantity goes to minus 1. So if you have alpha equal to 1, so this picture is saying if you have alpha equal to 1, then this thing will asymptotically approach -1. If you have alpha is some other value, it will asymptotically approach minus alpha. Okay? So in general, this will be minus alpha, right? Because as z tends to minus infinity, e to the z minus 1 tends to 0 minus 1 tends to minus 1. So alpha times that into minus alpha. Right? So this again theoretically converges faster, but this actually in experiments works slower than ReLU because you have to compute this exponent. So there is a non-trivial cost involved with the fact that the same thing we said about sigmoid and ReLU. If once in a while you have to do 1 plus e to the minus z, it's okay. But if you have to do it repeatedly, right, you have to do it for a large number of nodes and over a number of cycles, it all adds up. So the ease of computing a linear function actually beats the rate at which you converge better because you're using this nonlinear. So although this thing has theoretically better properties, when you implement it, it actually turns out to do something which is slower than using a normal value. Right? And then there is a scaled version of the same thing, right? Where you have a lambda here. So that this is an LU with this lambda term. So this picture on the right is the old LU picture. So you can ignore the picture. That's not a different picture. So now we come to this question which was raised before, which is this normalization, right? So this normalization initially was happening only that fan in, fan out normalization that we talked about earlier was only trying to preserve this variance at the beginning. After that, we could not guarantee anything about what was happening once training started. But it turns out that this scale LU actually self-normalizes, right? So it actually keeps the output of every layer as this kind of thing. Okay? So theoretically, this does something which is useful, which is that it keeps this variance from blowing up throughout the training period. But again, it's expensive to use because of this exponential. But this idea of normalizing as we go along, okay, was actually then, I mean, not then because this is a little later, I think this is 2017, but around the same time as this, there was the idea that maybe this normalization should be done anyway, right? So this is what's called batch normalization. So we have this idea of that we choose an activation function well, and we have a good initialization strategy. But now you don't want to have this variance kind of going bad on you during training. So the idea of batch normalization is to actually keep correcting for this. So what you do is that between two layers, you try to correct this by estimating the mean and variance for the current batch and then scaling. So what you do is you take the mean and the variance of each of the things that you calculate, right? And then you take each input, which is, remember, the input is the previous guy's output. So inputs are the same as outputs in some sense, right? Because every output of every internal node is the input of the next node. So what you do is if you have calculated the mean and the variance of the inputs across the mini batch, then you can take it and you can readjust. So what you're taking is you're recentering and you're reducing the quantity to make its variance normalized. Okay. So this is called batch normalization. And then after that, you don't want to make everything zero centered because that may be wrong, right? So you allow yourself to scale and shift it, and these parameters you learn. Okay? So this is a kind of correction that you're doing all the time. So between, so instead of feeding the output exactly as it is, you're doing this you're first converting it to a kind of normalized Gaussian with 0 and 1, and then you scale and shift it, right? So this is what is called batch normalization. And you learn this. So this part is just a function of your training, right? Whatever quantities you actually observe, you get the mean and the variance from that quantity. So these are observed quantities. These quantities, how much to scale and how much to shift, become parameters that you adjust in order to get better output. So lambda and beta in this scaling and shifting are learned parameters, whereas this part, this mean and variance of the observed mini batch is just what you calculate as you're running it. So now this mysteriously seems to work, right? So in particular, if you have used or looked at examples, in many of the inputs, and many times the input to a neural network needs to be standardized. For example, if you have, say, color values, which are in the range 0 to 255, right? You will often have to normalize them to 0 to 1, right? Or grayscale or whatever it is. So any type of color image input, very often the first thing will be to take the actual value and divide it by the range. So you get something on a scale of 0 to 1, and that's this normalization that you need in order for the network to not be using different scales at different points. Now it turns out if you use batch normalization, that happens automatically. So you avoid a little bit of work at the input layer, right? Now the main difficulty with this is this mean and variance is batch wise, right? So the mean and variance keeps changing with each mini batch. Even if you are doing it in one epoch, the thing will keep changing. So how do you get the mean and variance to use finally? Because finally you're going to have to run your network as before with some value. So one way is to just keep a average, right? You keep a moving average of the means and the standard deviations for each layer, and then you finally use this average value as your final scaling for that layer. So this is again something which does two things. One is it improves the speed of learning, and the other thing is it also does this regularizing. So it removes some of the generalization error. So the reason to mention this is that batch normalization is typically available, again, like many of these things, like we have discovered these different types of activation functions and these initializers. Batch normalization is available as a ready to use thing in a neural network library. So you can say apply batch normalization to this network and it will do it. So you don't have to get into the mechanics of how to do this calculation, because the mechanics will be done for you, but this is what is being achieved. Right? So this is so this now going back to somebody had this question before. So are we normalizing as we go along? Well, normally that initialization does only the variance correction at the beginning, but these kind of techniques, so either using that scaled LU, which I mentioned earlier, or explicitly, so this is just explicitly doing, so it's not accidentally doing it, it's explicitly doing this normalization at every point. Okay, so one last thing I will do today and then we'll stop. So this is something, again, the cost of learning, right? So since it is expensive to learn, you would like to exploit what you have learned. So it might seem that you have very specific problems, but if you look at different domains, then there are some intrinsic similarities between the inputs in those domains. So let's look at one which is fairly simple as an example, but I'll talk about it a little bit more. So in the image space, supposing you have already trained a network which can analyze and classify a large number of objects from day-to-day life, right? So this is a typical benchmark library for images, has this kind of thing. It will have some flowers, it will have some dogs, cats, some shoes, various things. Right? Now, supposing you want to build a new network, which is more specialized, right? It can only classify different types of vehicles, trucks, jeeps, cars, and so on. Now, of course, some of these occur over here, right? So there is an overlap because some subset of your old thing actually included vehicles. So it seems reasonable that there is some overlap in these two tasks. And at a more fundamental level, they're also doing similar things, right? Even though the category of objects you're looking at is different, it's a more specialized category in the second case. You're doing similar things, and the main point about these networks, as we will see, is that the layers, as we go from input to output, right? So in this picture here, we're going from input to output. So this lower is input and higher is output is kind of implicit in this pictorial thing. The input layer, the ones which are closer to input layer, are finding out in an image context, they are finding out some low level aspects of your input. So they are looking for things like edges and dark and light spaces and so on. And then as you go up this thing, they're trying to say, okay, is there a horizontal edge connecting to a vertical edge? Is there a curve? So the upper things are combining these things, right? So the lower levels intuitively identify, in an image setting at least, they identify more basic features of your image. Where are the boundaries? Where are the horizontal edges? Where are the vertical edges? And so on. And the upper layers look at how these are combining to decide what kind of an image it is. So now if you move from one class of images to another class of images, the intuition is that at the most basic level, the same things are being identified. Now, whether you're looking for horizontal and vertical edges in the context of animals or in the context of vehicles, it's the same horizontal and the same vertical. So whatever is those building blocks of these images tend to be the same. So it makes sense to try and reuse some of that work that you have already done. So that's this idea of transfer learning. So what you do is you take the existing network, right? And then you start a new network in which you essentially, at the lowest level, you use that network as it is. That is, you don't allow backpropagation to actually modify anything at that level. And you build now more layers on top of it whose parameters will be trained for this particular task, because those correspond to the actual classification task. Right? So the upper layers, it makes sense to change because those are the ones which reinterpret the combination of the lower features. So the different things that you're trying to identify, trucks from cars or something like that, then it might require a different level of discrimination compared to identifying a vehicle from an animal. Right? So one of them will have wheels and the other one will not have wheels, loosely speaking. But now among those that have wheels, you might have to look for 4 wheels versus 2 wheels. So you need a different level of discrimination in those lower level features. But once you have found wheels, you have found it whether there is a dog or a cat doesn't have wheels, or some other thing doesn't have wheels. Okay, so that's the idea of transfer learning. Now, how many layers should you use? How do you know that you should use 2 layers or 3 layers, or how many layers of the original network should you use? So one strategy is actually you kind of take the network as it is given to you, and you start from the top and you come down, right? So you say, okay, let me just relearn the 5th layer, see how it does. Then I say, okay, let me relearn both the 5th layer and the 4th layer and see how it does. So you keep allowing yourself to learn more and more layers from the top until you decide that, okay, now I have a compromise where the lower part is the old parameters and the upper part is the new parameters. So the real saving that you have is that you are kind of you're saving on relearning many layers. So you're really, so that's the idea of this transfer, right? So you're transferring your learning from one domain to another domain. So this is another technique to get over this. So these are all techniques from whatever we have discussed today, are all techniques which are helping to make this training process of a network more effective and more efficient. So here it's saying that, okay, you start with a new problem, don't approach it from scratch. Try to see if you can come up with an existing solution which has been trained for similar things and do it. Now, there are also strategies on how to do it if you don't have a similar problem, just take an arbitrary thing, but we won't talk about that, right? This makes sense, right? But at least if you're talking about the same type of problem, then if you have done some hard work before and trained a network to recognize the basic features for that problem, a similar problem in a different, slightly different domain, maybe those lower level layers are going to be useful for me now without relearning the whole thing from scratch. So that is this transfer learning. So I will stop with this. So what is yet to come? Okay, so back propagation itself. So we have this idea that we compute the gradients and then we apply a step. So how do you choose how much you change? So as I explained before, you could have this unstable situation where you kind of choose the wrong step and you keep going in the wrong direction. Or you choose too small a step and it will take you forever to just walk down this thing, okay, to the optimum. So how do you decide that step? Does it make sense to vary it and so on? So this is one set of techniques which people have developed to optimize the process of gradient descent and back propagation in a neural network. The other thing is that the whole idea is that of finding a minimum for the cost function, but we know that these kind of local search by using this gradient descent is essentially a greedy strategy. Right? It's saying that at this point, in which direction should I move in order to reduce my cost? Now, you could easily therefore gravitate towards a local minimum, which is not the best overall. So one thing we will address is this question, that is it a problem that, so if you look at simple linear regression, okay, so here there's a guaranteed there is only one global optimum, which is which you will find whether you use the closed form solution or you use gradient descent. But when I have this more complicated networks and a more complicated cost function that comes with that, I will have these ups and downs. And so I cannot promise you that there are, good minima which I will find always. So is this a problem? So this is one thing. And in general, we have this instability problem. Okay? So this instability problem partly comes because of these kind of strange shapes. So let me see if I can draw it. So you have this. So you might have some place here, okay, which looks like it is a zero slope place, but it's not actually a zero place. It's a kind of a saddle point, as they call it. Right? So these kind of issues can arise. So if you're relying on gradient descent to tell you the slope, tell you what to do, then will you get fooled into doing the wrong thing? So there are still many things to be done. So none of these is a guarantee, remember, of getting things resolved quickly. But these are all various strategies that have been used. And then finally, one which I did not talk about, which of course will be very important, is the network itself. What we have been assuming that we take a bunch of layers and we just throw them together by connecting everything to everything. Now, this is obviously wasteful in one way, because we are kind of forcing ourselves to learn a lot of connective parameters. So we said that, okay, if a parameter is not, if a connection is not useful, then ideally your learning should set that parameter to 0. So if you don't need an edge, it should ideally get a low weight. But you have to spend a lot of effort to discover that. So can you somehow anticipate this and connect your network more optimally so that you don't have to start with an assumption about a weight and then learn that it's useless? Right? So can we actually structure our networks better? So these are a couple of issues. So some of these we'll address next time. Then once we have looked at some of these, then we will look at some coding samples to see how these things are available in our libraries, so that you can also see that those hyperparameters are available to design neural networks, and what they mean now will become hopefully more clear. So I'll stop here, and if there are any questions, I can answer.
Excuse me, sir.
Yeah.
Sir, I want to ask about transfer learning.
Yeah.
So can it be used like if we have complete different scenarios, like if we have a pre-built model for classifying whether it's a cat or dog, and if we want to use it for recognizing, say, vehicles, like whether it's a car, bus, or what, so can we use it?
Yeah, so there are two parts to that. So, I mean, so if you're looking at images, which you are, then you're already in a good shape. I mean, if you then ask me whether you can use it to do sentiment analysis of text, then it's a very different problem, right? So if you're looking at images, there are two parts to it. So one is that the images should be of similar scale. If your assumption is that these early layers in your network, your lower layers are actually identifying shapes, okay, primitive shapes, as I said, edges or even squares or something like that, then the size of that thing matters. So one thing you will need to do is to ensure that the two classes of images, the ones for which you have trained the network and the ones for which you are going to use the transferred network, are of the same, roughly the same size. But beyond that, yes, the idea is very much that you don't have to rely on the fact that there is a significant overlap, unless the things are very different in, I mean, I don't know how to quantify this, but see, if the intuitively, if the recognition problem reduces to identifying some kind of shapes and similar features, then those underlying primitive things that make up shapes will be there, whether it's a cat or a dog or a cat or a truck. But if it is something to do with, say, different colors of dogs, right, then it may not be much use. So in a sense, it depends whether the conceptual, in your mind, the conceptual features that distinguish the objects share similar basic units, right? So, but it is definitely in that sense applicable across different domains, but there has to be some thread that connects them. They cannot be totally random. But some of these caveats there are applied, which is, for instance, that the images, if you're using images in both settings, then you should make sure that the images are roughly the same size. So you should not take very large images in one case and then apply it to very small images or vice versa, because that scaling also is a part of this feature, and that scaling should not distort your classification.
Okay, sir. Thanks.
So one more question.
Yeah.
So for ReLU in the positive side, the slope is always 1. That means the gradient in any direction comes out to be 1, right?
Yeah.
So doesn't that limit the learning rate, the learning of the network on the whole?
So usually, okay, so the ReLU I should mention is only used on internal nodes. So you will effectively have something at the output which is going to give you like a 0-1 category, right? So ReLU is not going to be used typically there. So there will be something which looks more like a saturating function at the output. So,
okay.
So that will mitigate this thing.
Fine.
Sir, I do have a question. For training this neural network, we are using backpropagation, which is this first order optimize, which solves the problem with this first order optimization method.
Yeah.
So
yeah.
if we use second order optimization, like we include Hessian also, can we expect to get training to bit faster or
yeah? So we will look at that. We will address that. So that is something to do. I mean, that will come up when we're talking about this unstable gradients. Yes, so there have been suggestions to use Hessian, as you said, as a second order gradient in order to estimate things faster. But the problem is that there is no corresponding. So the gradient matches this back. I mean, the back propagation is a kind of efficient way to calculate the gradient. There is no, unfortunately, there is no corresponding fast way to calculate the Hessian across a large network. So that's limited more by the computational aspect of it. How do you actually compute? So theoretically, yes, what you're saying is right. If you can compute second order derivatives, you can do better. But the practical difficulty is that there is no effective strategy known to actually use that in a large scale network. But we will look at that briefly, at least when we go to the next thing.
Okay, thank you.
Okay, so we'll stop and we'll have our next class as usual on Thursday. And the current plan is that maybe next week we will on Monday have a look at some examples which use all these things in some library. Okay, so that's the current thinking. So let's see. Okay, see you on Thursday.
Thank you, sir.
Thank you, sir.
Right.